Good evening, geometry students. So we've been talking all about ratios and proportions and similar polygons. We're going to talk about how to prove two triangles being similar. Now this is going to be very similar to what you've already learned with proving triangles congruent, but I just want to remind you that just because two shapes are similar, that does not mean that they are congruent. Those are two separate words. But there are still similarities between the two. So what I'd like for you to be able to do by the end of this lesson is to use angle, angle, side, angle, side, and side, side, side to show that two triangles are similar. Then, if two triangles are similar, I'd like for you to be able to find measurements indirectly by setting up proportions. So let's just jump right in and talk about these ways that we can show that two triangles are similar. So the first way is angle, angle, similarity. Angle, angle, similarity. Okay, if two pairs of corresponding angles are congruent, then we automatically know that the triangle is congruent. So we need two triangles and we need congruent angles. We need two pairs of them. So notice here in this image that A is congruent to D and B is congruent to E. So based off of the information I have, I know that angle A is congruent to angle D and angle B is congruent to angle E. Because I have two known angles being congruent to one another, I can then conclude, oh, triangle ABC is similar to triangle DEF. I am still being mindful, though, of keeping everything organized. So A corresponded with D, so A came first and D came first. B corresponded with E, so B was in the middle and E was in the middle, and so on. So let's go ahead and apply the angle-angle theorem in example 1. It says, explain why the triangles are similar and write a similarity statement. So right off the bat, hopefully you're noticing, oh, I know that two angles in these two triangles are going to be congruent. You're probably noticing angle A and angle D right off the bat. Why? Well, because they are both right angles. So I'm going to go ahead and say that angle A is congruent to angle D because all right angles are congruent. Now there's another pair of angles that I can easily tell are congruent, and it's your bow tie angles, so to speak. That's what I call them as a nickname, or your vertical angles. This angle is vertical to this angle. And remember, all vertical angles are congruent. So I can't just say this is angle C because there's a bunch of options that could be. So I need to say BCA, angle BCA, is congruent to angle DCE because they are vertical angles. Now I have two pairs of angles in each triangle that are congruent to each other. So I now know that triangle ABC is similar to triangle. Now be mindful to line this up. A corresponds with D because they're both right angles. So is similar to D, and then B is going to correspond with E, and C corresponds with C. So triangle DEC. So that was our first way to show that two triangles are similar if they have two congruent angles in them, or two congruent pairs of angles. The next way that we're going to show that two triangles are congruent is called side-side-side similarity. Now, there is a difference between side-side-side similarity and side-side-side congruency. Side-side-side similarity is going to have one big vocab difference in its definition. It says if all three pairs of corresponding sides are proportional, then the two triangles are similar. It does not say congruent. It does not say equal. So that's where the big difference is. With side-side-side congruency, I would need all the sides being exactly the same length. Now I just need them to be proportional. For example, what does that mean to be proportional? Well, what if this side were 1, this side were 2, and this side were 3? If this were proportional, then there would be a common scale factor between the two triangles. So for example, it might be tripled. So this one could be 3, 6, and then 9. Notice how the increase is by a constant factor or multiple. So I need to identify in my hypothesis that corresponding sides are in fact proportional, and proportional means that ratios are equal. So I know side AB corresponds with side DE. So I'm going to say AB over DE is equal to, and then let me get another color here. I know that AC corresponds with DF. And then for my third side, I have BC corresponding to EF. BC corresponds with EF. I put the small value over the large. Small value over the large each time. Now, I could have written this upside down, and that would have been fine. But remember, with proportions, keep them consistent. Now, because all three of my pairs of sides are, in fact, proportional, then I can say triangle ABC is similar to triangle DEF. Alrighty, we are moving right along. Let's talk about our third way to show that two triangles are similar. And remember, similar shapes are the same shape with congruent angles and proportional sides. They are not necessarily the same size, but the same shape. Okay, the last one is side angle side similarity. Side angle side similarity. In side angle side similarity, the theorem says if two pairs of corresponding sides are proportional and the included angle, so the angles in between the two sides that are proportional, if the included angle is congruent, then the two triangles are similar. So here what I want you to notice is this. AB corresponding with DE. Those are proportional. BC is corresponding with EF. Those are proportional. This angle B and this angle E are congruent. Not only are they congruent to each other, they are also in between the two sides. Okay, so that is the information that we have. So we have AB over DE is equal to BC over EF. So I said green over green, yellow over yellow for my proportion. And I also have angle B is congruent to angle E, which is the included or the interior angle, or not really interior, but it's in between the two sides. So my conclusion is triangle ABC is similar to triangle DEF. Alrighty, we're going to start applying these. So now I have angle, angle, side, 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 and side, angle, side. 3 ways to show that two triangles are similar. In example 2, it says verify that the triangles are similar. So you're going to need to look at the information that you're given in each of these to determine which way you're going to verify this. Are we going to use angle, angle similarity, side, side, side similarity, or side, angle, side similarity? It's up to us to determine. Well, based off of these pictures, I know the values of 3 sides of the triangle. So the only way I can do this one is through side, side, side. But how do I do that? I am trying to prove that all of the corresponding sides are proportional. So what I'm going to do, I am going to highlight for you guys just so you can see which sides correspond. Okay. I need to say that the relationship between these triangles is constant. That's what I need to say. So how I'm going to do that is by setting up ratios to see if the scale factor remains the same. So I'm going to put yellow over yellow, and I'm going to do large triangle over small triangle. You can do it the other way, but this is just how I'm doing it. So yellow over yellow, 3 over 2. What does that reduce to? If you put it into the calculator, you get 1.5. Now let's do pink over pink. That is 4.5 over 3. If I take 4.5 divided by 3, then I get 1.5. Now let's do green over green. I have 4.5 over 3. Well, I know that's going to be the same as the other one, but I'll still show you. All right, so I have 1.5, 1.5, 1.5. Notice how all of these match. They have to match. If they didn't, then we would not be able to keep going. But they do, so that means, yes, these are similar by side, side, side similarity. If one of these were to be a different number, then we would know that it would break that common scale factor between the two, so then they would not be similar. But because all of these match, that's why they are similar. Let's look at example B here. Look at the information that you have. Do you have enough information for angle, angle? Well, I only know one of the angles. You cannot assume that these are right angles because we don't have any markings. I only have 2 sides, and I don't have a way to figure out the third. Well, for right now, we don't have a way to figure out the third. So we have side, side, side is out of the question. We only have side, angle, side left. So let's kind of highlight what we've got going on. This side is corresponding with this one, yellow with yellow. And this side is corresponding with this one, green with green. And the angle that I'm given is in between those. So I've got 70 in the middle and 70 in the middle. It's just kind of small, so they drew it out, or they labeled it out to the side. All right. So now I'm going to have to show that the interior angles are congruent, which they are, or the included angles are congruent. So I know 70 equals 70, so angle D is congruent to angle H. We've got that part. I also need to show that the yellow over yellow is proportionate to the green over the green. So if I put 2 over 1, that equals 2. And if I put 5.8 over 2.9, that equals 2. Because they match, then I can say, yes, they are similar by side angle side similarity. Let me box in my answers for you. Okay. Let's look at example 3 now. It says, whoa, sorry you guys, didn't mean to bump the camera. It says, explain why triangle RSV is similar to triangle RTU. Then find RT. Okay. We are trying to show that this triangle, RSV, which is this smaller one right here, is similar to the larger one right here. We don't have enough information to say side, 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 and we don't have enough information to say side, angle, side. We're left with angle, angle. Well, I automatically have one pair of congruent angles that they gave me. But what I want you to notice is both of these triangles are butted up into this corner at the same time. They are sharing angle R. Angle R is in fact congruent to itself. So I know that these are similar by angle-angle similarity. They're similar by angle-angle similarity. Now that I know that they're similar by angle-angle similarity, I can use what we covered in the previous section about similar polygons. If two shapes are similar, then you can set up a proportion with them. So I'm going to say 8 over 12, because this right side corresponds with this right side. So this is 8 over 12 is equal to, so the small triangle over the large triangle is equal to 10 over the unknown RT. Let me say that one more time. The small triangle over the large triangle is equal to small triangle over large triangle. I just used corresponding sides to do that. So now cross multiply. I have 120 is equal to 8 RT. Divide by 8 on both sides, and that gets me RT is equal to 15. So this total length is 15. All righty, we have 2 more examples to do. So let's get those taken care of, shall we? In example 4, it wants us to find the length from B to A to the nearest tenth, but then it says, wait, are you sure the triangles are similar? We can only set up proportions if we know that the triangles are similar. And sometimes we have to use steps in order to get to the fact that they're similar. And we're going to use either angle-angle, side-angle-side, or side-side-side. So either angle-angle similarity, side-side-side, or side-angle-side similarity. Okay. So I have this larger triangle. I don't know. Let me kind of trace them both for you in the screen, hopefully to make you see it better. Okay. I have the larger triangle, ABC, and it is butted up with triangle FBG. They are both sharing the angle B. So I know right off the bat they have this pair or this angle in common to be congruent. I'm also given a very helpful clue in this image. These lines right here are telling me, hey, those are parallel. So that means I can treat this line kind of like a transversal, cutting parallel lines. So I can then conclude this angle, BFG, is congruent to angle A down here because they are in corresponding positions. So let me just do a quick little image of that down here just so you can see. I have 2 parallel lines. They are being cut by a transversal. Angles in corresponding positions are congruent. So I'm going to write that out. Corresponding angles are congruent. Just to remind you, because that was a couple chapters ago. So now in my triangles, I have 2 pairs of congruent angles. I know they're similar by angle-angle similarity. Now I can keep going. It wants me to find the length from B to A. That's what I'm trying to figure out. I know part of the length is 17, this part. And I also know the bases of each triangle is 6.5 and 24. So I'm going to need to set up a proportion. And remember, I want my proportions to stay consistent. So to keep those consistent, I'm just going to go ahead and say small triangle over large triangle, just so you know where I'm getting these. And remember, corresponding sides. So the small bottom or the small base is 6.5. And the large base is 24. So 6.5 over 24 is equal to, now I have my left side. There's only one part of this triangle that I need to figure out, and that's this part right here. I'm going to label it X because it is the unknown. So I'm doing small triangle over large triangle. What is the left part of the small triangle? Well, that's X. It's an unknown. Okay. How long is the left side of the large triangle? Well, it's 17 and X. It's not only 17. 17 only gets you to this point. So I have to take 17 plus X to get the rest of the way. So I've got 17 plus X. Now I have a proportion, and I can use that handy-dandy strategy of cross-multiplying. So this is going to get me, let's see here, 110.5, 6.5 times 17. Actually, hold on, you guys. Let me go ahead and write it out like this. I've got 6.5 times 17 plus X is equal to 24X. Distribute your 6.5, which is going to be 110.5 plus 6.5x equals 24x. Subtract 6.5x from both sides. So that gets me 110.5 is equal to 17.5x. Divide by 17.5 on both sides. And when you round it, you're going to get x is equal to 6.3. So the hardest part, I think, of this problem is just knowing how to set up the proportion and getting everything lined up. After that, you just cross-multiply and solve like any regular equation. Okay, we're going to use similar triangles one more time in this example, and then that is all for today's lesson. So it says, a tourist wants to estimate the height of an office tower. He places a mirror on the ground and moves away until he sees the top of the tower in the mirror. Using the information in the given image, what is the height of the office tower? So this is a strategy where you can place a mirror and it will create similar triangles if you don't have any other way to kind of measure things. So I know that this small triangle right here is similar to this larger triangle, and I am going to correspond the short base with the short base right here. And I'm going to correspond the height of the small triangle with the height of the large triangle. Now, there is one little detail in this image that I don't want you to forget or overlook. This is in meters. This is in meters. This is in centimeters. I'm going to convert this to meters. So 192 centimeters is 1.92 meters. So I'm just going to cross that out so I don't accidentally use that number, because I like to keep everything in the same unit. Now I need to decide how I'm going to set up my proportion. Don't let all the word problem stuff confuse you. You have two similar triangles, so you set up a proportion, and you set that proportion up by keeping it consistent and lining up corresponding parts. So I'm going to do small over large, like the small triangle values over the large triangle values. And I'm going to do pink over pink first. So this is going to be 0.4, the base of this one, over the base of the big one. So this is going to be 0.4 over 87.6. Let me make sure that's in the screen for you. Is equal to height over height, or green over green. So that's going to be 1.92 over my variable x. Cross multiply. You're definitely going to need to get a calculator out for this one. So I have 0.4x is equal to, when you multiply these two guys together, I got 168.192 in my calculator. Isolate x the rest of the way by dividing by 0.4. And that gets us x is equal to 420.48 meters. In other words, the height of this building is about 420.5 meters, about. How did we do that one more time? We set up a proportion because we knew that they were similar. We put the base over the base and the height over the height, cross-multiplied, and solved. I hope this is making sense. I hope you have a great night, and I'll see you later.